Welcome back to Applied Algebra and Trigonometry. We're going to be talking today about linear equations and graphs. And now it's time to play the game of the semester. Is it linear? Contestants will please remember that an equation is linear if each term contains only one variable to the first power or the term is a constant. I will present you with 7 equations. Please record on your answer sheet at home whether or not each equation is linear. Ready? Begin. Number 1, g equals 3t minus 2. Number 2, x squared minus 6x plus 5 equals 0. Number 3, 3x plus 3y equals 6. Number 4, x plus xy minus y equals 7x. Number 5, 4 divided by v equals 5w. Number 6, 2 times the quantity x plus 3 close parenthesis equals negative 2w plus z. And finally, number 7, the square root of x plus g equals 3 minus g. Which of those are linear? It's time to reveal the correct answers. But as we do, let's go ahead and analyze each of these equations. Let's shrink the screen just a little bit so everything will fit. Okay, is it linear? Is number 1, g equals 3t minus 2 linear? The answer is yes, it is linear. How many variables are there in each term? There is one variable in this term, one variable in this term, no variables in this term, but that's okay because it is a constant. All right, so number of variables in each term, answer is 1, or the term is a constant. So actually this is 1 or 0. All right, what are the variable powers, aka exponents? For each of these, there is a power of 1. How do we know it's a power of 1? Because we see the variable, but we do not see an exponent. We do not write a variable of 1. So in each case, those variables have a power or an exponent of 1. For number 2, is that a linear equation? No, it is not. How many variables are there in each term? There's one variable here, one variable here, and here is a constant with no variables. So we have one variable or none in each term of that equation. What are the variable powers, though? Take a look at the very first one. We have an exponent of 2. And then on the second term, we have an exponent of 1, but too late. Once you have an exponent greater than 1, that's it. Some of you may have noted another exponent of a variable in there, but we'll save that for later. Is number 3 linear? Yes, number 3 is linear. Take a look at it. We have one variable, and a constant. The number of variables in each term is 1 or 0. What are the variable powers? Take a look at them. They are all powers of 1. Is equation 4 linear? No. Why not? The highest exponent of any variable in there is 1. Take a look all the way across. Where is the problem? The problem is here. Each term contains only one variable in a linear equation. This has 2 variables in the second term. So there are 2 or 1 variable in each term. This is the problem. It can only be 1 at the most. All right, number 5. Is that a linear equation? That one looks a little different. The answer is no. There are different reasons for this. One of them is, what's the exponent of v? For those of you who really know your exponents, you could rewrite that equation In this way, you could rewrite number 5 as 4v to the negative 1, where automatically that is not a positive 1. You have negative there. The other way you could look at this is do a little algebra on it. If you multiply both sides by v, you're going to get rid of it, v, that is, on the left-hand side. You'll have 4 equals 5wv. That means in this term, you have 2 variables. So for all those reasons, this is no. For now, just remember if you have a variable in the denominator, it is not a linear equation. Number 6, yes, that is a linear equation. Whether you look at this first side over here as one term, because it is, you have 2 times whatever's in the parenthesis, that's one term, or whether you decide to distribute that 2, so you get 2 separate terms. In each case, you either have a term with one variable, or you have a term with one variable and a constant. And on the other side, you have one variable in this term and one variable in that term. And the highest power of a variable that you can see in this equation is 1. It is an equation in 3 dimensions, which we're not quite going to get to in this class, but yes, it is still linear. And for number 7, the answer is no. There is either one variable or 0 variables in each term. However, if you look closely, you have here a square root of a variable, which is the same thing as writing x to the 1/2. But if you want to get rid of that square root, move up everything to the other side and square both sides. Since g has an understood exponent of 1, g doesn't disappear when you move the g's to the same side of the equation. You're going to have to square a g, which is, once again, higher than the variable powers that are allowed. So yes, you could have 1 here, because that would be the power of g, perhaps, or you could have 1/2 as it's written now, or you could wind up with a 2. So because you can rewrite this in one way or another, you're going to have an exponent that does not equal 1. This equation is nonlinear. And that's all for today for Is It Linear? But stick around, there's more video to come. Thank you for playing. All right, here's a linear equation. We can solve this for f, or we could solve this for g. To solve it for f, we're going to add g to both sides. And while we're at it, let's go ahead and subtract 6 from both sides, because that will give us 3f equals g minus 6, and then we just need to divide by 3 on both sides. That gives us f equals g minus 6 over 3, or if you want it in a more familiar form, 1/3 g minus 2. Okay, but we have solved it for f. We have isolated f on one side. Let's do the same thing, isolating g to solve for g. Since we have a positive 3f on the left, we're going to subtract 3f from both sides to move it over. We are going to do the same by subtracting negative 6. It will move 6 out of the way. All right, so we now have be careful, a negative g equals negative 3f minus 6. And now we have to get rid of that negative, because not only do we want to isolate g, we want to solve for positive g. We have to finish with just g, no negative. So on this side, we'll have 3f plus 6. I hope some of you saw the quicker way that could be done. When I solved for f, I mentioned that that should look familiar. The reason it should look familiar is it is in this form, the slope-intercept form of a linear equation, y equals mx plus b, where we have these two variables. We have an independent variable and a dependent variable. Yep, we are going to come back to those terms again and again and again. All right, we have some other things going on here, though. We also have this m, which represents slope, and we often say this b represents the y-intercept. However, it actually only represents the y term of the y-intercept, which is a point which should have an x and y value. It only has a y. Decision time. Get technical or not? Nah, we're just going to call it the y-intercept. Let's analyze what we have here when we're looking at the equation f equals 1/3 g minus 2. Written this way, what is the independent variable? G. What is the dependent variable? F. What is the slope? 1/3, 1/3. What is the y-intercept? -2. All right, let's analyze our other equation. What's the independent variable? F. What's the dependent variable? G. What's the slope? 3, or 3/1. And what's the y-intercept? +6. So if you are given a linear equation in two unknowns, you can convert it into slope-intercept form and read the slope and the y value of the y-intercept right off the equation there. But what if you know the coordinates of 2 points rather than the equation? Can you find the slope and the corresponding equation? Sure you can. You remember how to do that, just like this. Here are 2 points on a Cartesian plane. They are 12, 18 and 32, 8. X always comes before y, and I'm just going to choose to designate this one as x1, y1, and this one as x2, y2. You can do it in the opposite way as long as you are consistent with how you label them and how you use them in this formula. Slope, the formula for slope, which in our equation is m. The formula for slope is actually the distance that the line rises over the distance that it runs. In other words, the distance in the vertical direction versus the distance in the horizontal direction. One way to remember that slope is rise over run, rise always coming before running, is you have to rise up out of your chair to run away from this silly video. You have to rise before you can run. And once you have calculated your slope and are getting ready to read it, always let the numerator tell you whether to go up or down. Up if it's positive, down if it's negative. And then let the denominator tell you how far to go from left to right between one point and a second point on the line. But how do we actually go about finding the slope between these 2 points? Well, the formula for slope, the formal formula, is y2 minus y1 over, now be careful, do not mix up the order. It's over x2 minus x1. So here is one point, and here is the other point. Don't confuse those. For the points that are on the Cartesian plane, y2 has been assigned to the value 8, minus y1, that's 18, over x2, which is 32, minus x1, which is 12. So that will give us a -10 over 20, or a -1/2. So if we were to go down 1 and over 2, and down 1 and over 2, and down 1 and over 2, we would wind up at points on that line. And eventually we would wind up at 32, 8, and we could continue. Here's another example for you. Pause the video for a moment to see if you can calculate the slope. Remember to bring in the value of -1 from where you have it over here in the coordinate pair. Do not drop the negative. This becomes 4 over 2, or 2. Notice that our first slope was in this direction. That's what the line looked like approximately. And for our second example, we have approximately this. And those lines look different. They're still linear. Well, One of them's kind of crooked, more crooked than the other. But what we have here are a negative slope and a positive slope. Which one is which? Always read your slope from left to right as you read a book. A negative slope always goes downhill when you're reading the line from left to right. Or in other words, m is less than 0. It's negative. On the other hand, a positive slope rises as you go from left to right. Positive or m greater than 0. Those are two different ways to indicate such a slope. What about some other strange cases? What about a horizontal line or a vertical line? So let me ask you this. Is it possible for you to walk on a horizontal surface? Can you do it? Sure, you can do it. Yeah, that slope of that horizontal surface would be m equals 0 if it's perfectly horizontal. You can walk along that, it's possible. It has a slope, it just happens to equal 0. However, unless you are Peter Parker or Miles Morales, you are not going to be able to climb up a vertical wall. We indicate that a vertical line has no slope. How can we say that? Well, let's imagine 2 points on a vertical line. I'm going to go back up to my graph here, my coordinate axes, and I'm going to put this line at x equals -2. So every point on here has a value of x that's equal to 2. For instance, I have the points -2, 0, and -2, -2, right here and right here. So let's calculate the slope for that. I get a little slightly bigger pen. Okay, the slope here, m, equals, let's see, the difference in the y's, 0 minus -2 over -2 minus -2. Okay, difference in the y's over the difference in the x's. So I get 2 on top and I get -2 plus 2 on the bottom, or 2 over 0. We cannot divide by 0, therefore we cannot come up with a value for slope, and we say there is no slope of a vertical line. A couple more tips for you. If -1 is less than m, which is less than 0, then you have a gradual negative slope. And if 0 is less than m, which is less than 1, you have a gradual positive slope. Gradual meaning not steep. Of course, the slope-intercept form of an equation is very useful when it comes to graphing an equation. So here I'm going to find the intercept of the y-axis, and that's 3/2 is equal to 1.5. So there is where this yellow line, first equation, passes the y-axis. Now, is it positive or negative slope? What do I do? Well, this slope tells me that I need to go down 1 whole unit because it's a negative slope, and then I need to go to the right 2 units. So this is going to be a little bit tricky because I'm at a half unit. So I have to come down 1 whole unit and then over 2 whole units. So there's my next point. And then down 1 whole unit and over 2 whole units there. And I can continue this process to draw this line with its negative slope. Let's do the same thing for the next equation. The y-intercept is 3, 1, 2, 3. That's where I'm starting. Now I have a positive 2x, which is the same thing as 2 over 1 for my slope. So I'm going to go up 2 because it's positive, and then I'm going to go to the right 1. I always go up or down according to the sign of the slope, and always go to the right according to whatever's in the denominator. So here I have my second line. I'm going to make this a little bit bigger so we can see those points easier. The problem with doing that is it makes it very obvious that I kind of messed up the purple line. It does not exactly go through that point, the y-intercept. Please pretend it does, and we will move on. Now I'm going to label that y-intercept as the point 0, 3. And what is the next point I come to? Well, the next point's right beside it. And the next point's right beside it. Infinitely close, in fact. But the next one that I actually graphed to draw this is 1, 5. And there, I have labeled 2 points on the yellow graph, the first equation. Now the thing about these lines indicate all of the points, all of the combination of x, y values that will solve this equation. In other words, will make it a true equation. So let's see what happens if we put them in. Okay, let's take 0 and 3/2 first. If I put in 3/2 for y, and that's equal to -1/2, what is the x in that for that point? It is 0 plus 3/2. So I get 3/2 equals 3/2. Well, that's kind of obvious. Let's try another point though. Let's take the point 2 and 1/2 and put it in here. The 1/2 is the y value. Then we have a -1/2. What's the x value? That x value is 2. And I'm adding 3/2. Okay, 1/2 equals -1/2. Oh, I'm multiplying by a fraction, so I'm going to write 2 as 2 over 1. And then I get 1/2 equals -1 plus 3 over 2. But you know what? And this is one case where I really don't want to cancel. Instead, I'm going to multiply straight across. -1 times 2 is -2, and that's over 2 times 102. Now I have 1/2 equals 3/2 minus 2/2. That's 1/2. It checks. In fact, for any point that you choose on this line, you can plug it into this original equation of your line, and you will always get a true value at the end, a true statement. Let's work with the other equation now. So we're going to put 0, 3 in first, okay? 3 is the y value. That equals 2 times the x value of 0 for this point, 0, 3. And finishing the equation, plus 3. So 3 equals 3. If instead I put in the point 1, 5, the y value is 5, and the x value is 1. So 5 equals 2 plus 3. Is that true? Yes, because 5 equals 5. See, I have a true statement here. Those 2 points are on that line. Every point on that line will make this equation into a true statement. But did we forget the x-intercept? So far, this y-intercept has gained all our attention because we know that the y-intercept is simply the place where x equals 0. And if you plug x equals 0 into that equation, you solve for the y-intercept. 1, 2, 3, there it is. Okay, what about the x-intercept for this equation? Well, let's think just a little bit more about what that y-intercept means. If we make a t-chart, a t-table, where x is 0, y equals 3. Well, what happens when y is 0? If y is 0, the point that corresponds or has a y value of 0 is going to be on that x-axis. It is going to be the x-intercept. So all we have to do is plug 0 in for y. So we take 0 equals 2x plus 3. That's what our original equation becomes. And now we need to solve for x. So let's subtract 3 from both sides. Minus 3. We'll get 2x equals -3 and divide by 2. So x equals -3/2. That is the x-intercept. Have to deal with a fraction, but that's okay. We can do that. So there's 1, 2, 3, but it's at negative 3 over 2, not positive 3 over 2. So 1, 2, 3. Negative 3 halves would be about right here. Negative 3 halves, 0. That's the x-intercept. There's our line. Now, remember that I told you your TI-89 graphs by forming its own internal t-tables, x and y values? Well, if you need to graph a linear equation, 2 points you would be very wise to use would be the x and y intercepts. To get the y-intercept, plug 0 in for x. To get the x-intercept, plug 0 in for y. For this equation we just did, when we plugged 0 in for x, we got 3 for y, and when we plugged 0 in for y, we got negative 3 halves for our x value. We will discuss these concepts further in class with a little more difficult examples. I'm hoping this was a lot of review for you. Review's a good thing, and you will need all of these skills as we progress in the class. By the way, if you liked the peppy music earlier in the video, check out the link I have here on this end card.